Okay, good afternoon, everyone. So this is lecture 9. And today we're going to wrap up the discussion of GPIO, general purpose input and output. And this is really the basic tools that we need to get comfortable with before we can move on to more complicated, more interesting, more useful, and more fun applications. And so we're going to be talking primarily about the input side of GPIO. But I want to spend some good time just talking to you about the switches that you have in your kits, because from talking to some of you, I know that there's some confusion about how to hook up these switches. And so before I kind of go into that, let me just sort of roll you back to what the title of this course is. You know, it's Intro to Embedded Systems, right? And I want to emphasize the word systems there for just a minute. So what's a system? You can think about a system as a set of interacting elements, components or subsystems or parts that's designed to get some job done. And when you think about a system, the key point there is that it means that there are a lot of parts. And so really this course is an introduction. On the one hand, you're learning C and you're learning about these various microcontrollers, but it's also an introduction to systems thinking, which means how do you really envision and how do you successfully put together something that has a whole bunch of pieces to it. And it's not just the code. This is not a coding course, right? It's not a software course, because there is the code, which is an important part of it, but there's also the hardware, the chip itself. And then there are also all the things that we have to hook up to that hardware so that we can sense things and then we control things. And also part of this whole system is the programming environment that you had to put on your computer, whether it's Visual Studio Code or the compilers, the tool chain, make file, and all that kind of stuff. So really this course is about exposing you to what happens when you have a fairly large and increasing number of things, of parts that have to all go together and they have to all work together in order to get a job done. And so I'm going to come back to this theme later on from time to time. But I wanted to sort of emphasize that point because today I'm going to be talking about in some detail just about one of the parts that you've got in your system, which is these little switches. So I'm going to talk about those in some detail. Okay, and to guide us in that, I'm going to show you this demo. I'm not going to show you a video of it, but I'm going to show you it in a bunch of slides. And this is an application that I built. It's a pretty simple one, and it describes it up in the top right. We're going to turn on some LEDs when buttons are pressed. So you can see in the figure, I have a left button and a right button, 2 buttons. And when I push my finger on the left button, the red LED will go on. And when I push my finger on the right button, the green LED will go on. Now, you don't need an Arduino Uno or an Atmega 328P microcontroller to do something like this. You could just do this with hardware and leave out the whole microcontroller. But I just show you this because it's an illustration of a system as an increasing number of components that you have to know how they all work, and they all have to work together to get the thing done. So, and also, if you can do this, this sort of takes you quite a ways toward being able to do your homework assignment, which is lab number 2, which is due a week from tomorrow. And for those of you who were looking for it, the link is up on Moodle for turning in your lab assignment number 2. But okay, so this is the circuit. This is the hardware part. There's also code that runs this, and I'll show you that on the very last slide in today's deck of slides. So I'm going to spend almost half of the lecture just talking about this circuit, okay, how it works and how you hook it all up. And so I want to spend some time on the little switches. All right, so the little momentary push button switches that you have in your kit, so you each should have 3 of them. And there's they'll only fit on the breadboard in one of two different positions. But it's easy to wire these things up the wrong way if you don't have a sense of what the wiring diagram is. And we don't have a data sheet for them that came with them. So I provided this information for you. So first of all, the switches that you have, they're not square, they're rectangular. So that, and I say that because some of these push button switches are square, and it's a little harder to find out which lead is which on the square ones. So these are rectangular. They have a narrow dimension, and then they have a wide dimension here. And so I'm just numbering them. And what this thing here represents is the channel or the gap inside the breadboard. You know, that's this thing here. Okay, that runs the length of the breadboard. And so the wide dimension will straddle that gap when you push these into the breadboard. So that's the first point. Okay, that's how they go into the breadboard. Now, the next thing about them is that these are single pole, single throw switches. And as you get on and do more things in your ECE career, you'll be experimenting with you'll be experiencing a lot of different kinds of switches. Single pole, single throw just means that it has one pole, which means in essence, one input and one output. There's just one pair of connections. And that pair of connections is either made or broken. In other words, it's sort of on or off. And the thing about the two poles, right? One of them is this pair of connections 1 and 2. So these two are connected together internally inside the switch. And then likewise, 3 and 4 are connected together internally in the switch. And then what happens is when you push the button down, you're actually making contact between those two sides. So when you take that thing and you push it into the breadboard, as I've shown it, right, you see that I have an orange wire that's going in to connection 1. And then I have a black wire going into connection 4, and they're on opposite sides, you know, across the width of this thing. And when you press down on that switch, you'll make electrical contact between the yellow wire and the black wire. Okay, so I just wanted you to be sure to have that so you can hook these things up the right way. And now let's go and spend some time looking, analyzing, and describing this circuit that I'm showing you. So you see the photograph of the thing on the left, and then there's a schematic drawing of that on the right. So just let's take a minute to get familiar with what's happening on there. So obviously you've got the Arduino, you know, the photograph of the Arduino on the left, and then I've got that shown in a box on the right. You know, here's the Arduino here, okay? And coming from the Arduino, I'm taking out two things. I'm taking out 5 volts, that's our VCC, that's our positive voltage for our circuit. So I'm taking that out in a red wire, and I'm also taking ground out in a black wire. And then what I'm doing is I'm connecting those to the breadboard using the voltage rails on the breadboard. So now what does that terminology mean? Maybe you're familiar with it and maybe not. But you know, within one of these breadboard, if we look at where that red wire connects, right? We've got a red wire going from 5 volts on the Arduino, right? And then it comes to this top horizontal row. And then within the breadboard, connected all the way down this line, there's actually a piece of metal underneath. So it provides connection all the way down that line. You call that one of the power rails or the voltage rails on the breadboard. And since it's closer to the red wire up on top of the breadboard, right, then by convention, we would call that our positive voltage rail. So that's our 5 volt rail on the breadboard. That's what's represented by that red bar, the way I've drawn it, okay? Then we have the black wire that's going to the ground rail on the breadboard, right? And that's what's shown down here. So now that we're oriented there, you can see I've shown sort of this kind of thick red and this thick black lines here. Those represent the voltage rails on the breadboard. And now let's just make the mental connection between the photograph on the left and then the schematic on the right. Okay, so interacting between the breadboard, between the solderless breadboard and the Arduino, we have 4 pins. They're D3 and D4 are input pins, and D6 and D7 are output pins. And I've shown the input pins, here as, kind of an arrow pointing in, and the output pins are arrows pointing out. And I've kind of, instead of having D3 and D4 right next to each other, and then a gap, and D6 and D7 a little farther away, which is the way they naturally, the pins are, I just took the liberty of grouping D3 and D6 close together because that's the red LED part of the circuit. And then D4 and D7 are the green LED part of the circuit. Okay, and so let's just kind of follow some of this. So look at D7, right? Let's look at this one, and let's just follow that whole circuit. Going back to the photo, D7 would be this wire here. Okay, it goes from pin D7, that's pin 7 of port D. And you can see it's connecting here, and then it's connecting to a resistor, other end of the resistor, then it's going to one lead of the LED. It's the anode lead or the plus lead, and then it goes to ground. And then I've represented that whole thing here. Okay, and then I'll look at the switch that would control that via the Arduino. You've got that orange wire that's going to one terminal of the switch here. And then on the opposite terminal of the switch, I have a black wire going to ground. And that's what's represented, here. Okay. And so that takes care of the right push button, which I'm calling S2, and the green LED. The left push button and the red LED, everything is the same, except notice that I put this resistor in here. I stuck a resistor in here because I want to show you the placement of an external pull-up resistor. And I'll tell you what that means. But where's that resistor connected? It's going between that yellow wire, right, which is our D3 input, and then it's connected to my plus 5-volt rail. So that's what's shown right here. You see, I have that plus 5-volt pull-up resistor. And so an upshot of this whole thing is you don't need to have an external pull-up resistor because you have internal pull-up resistors inside the Arduino Uno ports, provided you activate them. If you don't have pull-up resistors, internal or external, you'll end up with floating inputs. They'll have undetermined values, and the system will behave erroneously. So now, before I go any further, someone give me a reaction. Is this stuff all stuff you've already seen and you've all known for a long time, and I don't need to spend time on this? Or is this helpful and new, this level of detail? Did I hear helpful and new?
It's all helpful and new from the students in this room.
Okay, good, okay, good. So now I'm going to go to the next slide, and I'm going to leave behind the photograph, okay? And I'm just going to use the schematic, okay? So at this point, I'd like us to be able to understand the schematic as a schematic representation of the photograph. And I just want to start to get into some of the code for hooking this thing up, okay? And so we know that the Arduino has these pins, and the pins can be used as inputs or outputs. Indeed, D3 and D4 are going to be inputs, and D6 and D7 are going to be outputs in this application. So how do we configure this? Well, we have to set the pin direction, okay? And so to do that, there are a number of ways that we could do it, but I could use this command DDRD, that's data direction register D, and then I could give it the binary value 0x11000000. So I've put ones in the positions for D7 and D6, and I've put zeros in all of the other positions. What that would do is it would make D6 and D7 outputs, and it would make all of the other pins inputs, okay? Now, if you look at the problem, the design of the thing, we're only making use of 4 of those pins. So we really only care about, we want 2 of them to be inputs and 2 of them to be outputs. What do we do with the rest of them? Well, by doing this DDRD here, right, we're assigning all of them to be input or outputs. It's just that D6 and D7, the 2 uppermost bits, they're going to be outputs because we put ones in those positions, and all the rest are going to be inputs, okay? Now, another way to write this is to write it like this. DDRD is equal to one shift left DDD6 or one shift left DDD7, which is exactly the same as writing DDRD is equal to one shift left 6 or one shift left 7. I'll tell you in a minute how that works, but know that these are identical. As far as the microcontroller is concerned, these two lines say the same thing. That's because, as I mentioned before, we do have a statement that says define DDD7 as 7. And then there's also define DDD6 as 6. This is tucked up in this include avr/io.h file that you put at the top of all your code that does many things, including these define statements. So that when it's compiling, all right, the first step in compilation is really the pre-processing. And what that does is it'll go through all the text in the source code. Every time it sees DDD7, it replaces it with 7. Every time it sees DDD6, it'll replace it with 6. So that's why these two lines are identical here. And it's once you get more comfortable and you understand it, you'll see that this one is sort of self-documenting. You'll sort of get into the habit, many of you, and you'll say, okay, I sort of, either of these will work, but I'm getting more comfortable with using that middle one as a way of documenting and increasing the understandability. So we could either use DDRD is equal to 0x11000000. That'll work. It's just hard to see all the ones and zeros. Okay, this one down here, why does that work? I mean, why does that cause pins 6 and 7 to be outputs and the rest to be inputs? Well, let's break that down, right, piece by piece. Question.
Yes, we have a question in the room.
Yeah.
So for that DDRD equal to 0x, and the rest of zeros, how come it's not 0? Like, why 0x?
0x says that this is a binary number. Good question. If I didn't have the 0x, if I just wrote DDRD equals 11000000, that would be a decimal number. All right, so I would have entered the number, looks like it's 11 million, right? I think it would be 11 million, right? It's when you put 0x in front of it, you're saying this is a binary number that I'm about to type in. Repeat?
He thought 0x was hexadecimal and 0b was binary.
Oh, you're right. You're absolutely right. Thank you for catching that. That should be a B. B. You're right about that. So to continue on, why does this work? When I write one left shift 6, right? What I'm really doing, sort of picking up with that conversation we just had, 1 is decimal, right? So if I just write 1 without a 0b in front of it, it means decimal, right? But 1 decimal is the same as 1 in binary. So it's sort of a special number. 1 is equivalent to this bit pattern, 00000001. And if we shift that left 6 times, we end up with this. So we end up with a 1 in bit position 6. Remember, there's bit position 0 through bit position 7. Okay, and if we do 1 shift left 7, we end up with a 1 in bit position 7. And then when we OR those two together, we get the result that we want. So that's why this works. That's why this shorthand works for us. It's complicated to learn, but once you get the hang of it, then it becomes, eventually it sort of becomes second nature-ish. Okay, so that's the part about just setting the pin direction. Now, let's talk about turning the LEDs on and off. I want to talk about inputs. I want to talk about reading those buttons. We'll get to those, but let's spend a minute talking about how do we turn the LEDs on or off. There's going to be an if statement that says, if the button is pressed or if the button is not pressed. We'll get to that. I just want to show you the code that just serves the purpose of causing those LEDs to go on or off. So let's take a look at this first one. To turn on the LED, the red LED, okay? So you see the red LED here is connected to D6, right? So we have to make that go high, 5 volts, right? And so the way we would do that is we do port D or equals 1 shift left port 6. What that will do is it'll put a 1 in position D6, and it will OR that with the previous value of port D. So when we do port D or equals, right, what we're saying is port D equals port D or 1 shift left 6. So we'll take whatever value port D had before, and it's going to OR that with a 1 in bit position 6. It leaves all of the other bits of port D unchanged. That's an important thing here. Okay, so I want to just note that. These LED instructions here, right, they leave all the other bits of port D alone. Okay, here I'm referring to these instructions here. So we're using the sort of, you know, the complicated shorthand port D or equals. That leaves all the other bits alone. Okay, that's to turn the LED on. How do we turn the LED off? Well, we use this nasty bit here. That turns off the red LED. Now let's unpack that to see why that causes the red LED to go off, and it leaves all the rest of the bits in that byte untouched. Okay, so the red LED is pin D6. Okay, so we have to talk to, we have to set pin, port D6, right? In register port D, we have to set that to 0. So let's break this down. Let's look at what's happening here, right? What we've got is the complement, that's the tilde, the complement of 1 shift left 6 times. Okay, and so here's 1 is just a bunch of zeros followed by 1, and then we shift that 6 times, that gives us this. But we need the complement of that. And so then the complement of that is just, is all 1s, but with a hole in bit position 6, or a 0 in bit position 6. So what this bit of code here does, right, this here, port D and equals all that. So it's port D equals port D and 1, 0, and a bunch of other 1s. So it's whatever value port D previously had before this instruction, we're going to AND that with a bunch of 1s and a 0 in one of the positions. And that will leave all the other bits alone, but it'll 0 out position 6. Okay, so that's why we need it. We need the complement so that we can, go from, someone asked, why do we have a complement? Well, we have the complement because, the shifting gives us this line here, right? The shift operator conveniently puts a 1 in a particular position. But what we want is a 0 in that position and a 1 everywhere else. So the complement does that. Okay. So we've looked at how to set the pin direction and how to turn the LEDs on and off, okay? Now, reading the input pins, all right? We're going to get to that in a few slides. We'll get to it. But before we do, I want to go back and look at the hardware, okay? And we'll make sure we understand the hardware and the switches, and then we'll look at how to write code to read those input pins. Okay, so so let's now analyze, sort of, understand the circuit, because we want to see how it is that the buttons make D3 and D4 high and low, because that's what we want to happen when, D3 and D4 are our inputs, right? And then I've got these switches here. And when I, press or release that the button on that switch, I want to cause D3 or D4 to go high or low. Okay, so let's look at switch S1 first. We'll start out with this one. Okay, and we'll look at first the case where the switch is open, and that's the way it's shown, right? It's shown an open connection between the terminal. I mean, your finger is off the button. Okay, and so when that's the case, when your finger is off the button, S1 is open, what's the value of D3? Well, what you'll see is that D3 is, what it experiences is a resistor here up to 5 volts. You call that a pull-up resistor, okay? So we have this external pull-up resistor on S1, and it's going to make it's going to make D3 equal 5 volts when that switch is open. So that's what's happening right here. Okay, when your finger off the switch is open. Okay, and you have D3 experiences a pull up to 5 volts through that resistor. So we have this value right here. Okay, now we come along with our finger and we close the switch. So I'm going to close it like this. All right, and when I close the switch, what I'm now doing is I'm taking D3 and I'm connecting it directly to ground. Okay, so at that point, I have D3 is grounded. So you can see that with the action of the switch and the pull-up resistor allows us to finger off the switch, D3 is pulled up high, and finger on the switch, D3 is pulled down to ground. Okay, now let's look at switch S2. So let's concentrate on S2 here, all right? Focus on this one here. Now S2 does not have a pull-up resistor, okay? So note that, there's no external pull-up resistor on S2. So what does that mean for the case when the switch is open? Before we put our finger on the switch, no finger on the switch, what's the value on D4? Well, what you can see is D4 is just going into an open circuit. It goes to one terminal of the switch, then it doesn't go anywhere else. So it's neither high nor low. Our external circuit is not forcing any value into D4. So we say that that's floating. We call that a floating input because it's not connected high, it's not connected low. So what value will it have? If you were to approach this with a multimeter, right? If you've got a multimeter, a voltmeter, and you connected the black lead of the multimeter to ground and the red lead of the multimeter to D4, what would you read? Would you read 0? Would you read 5? You don't know. It depends on what's happening inside the Arduino Uno. Okay, so you have to be careful when you configure something with a floating input like this. I'm going to show you what happens on the next slide. It turns out that you can configure all of these ports to have an internal pull-up, and so you need a pull-up resistor either internally or external to avoid having a floating input, because a floating input you're just going to have it's undetermined. Okay, so let's go back now and talk about that's hardware. Everything. So this was all the hardware. Now let's go inside the chip. Okay, we're becoming, we're looking at software now, right? And so remember, we've seen this many times. We've been talking about the pins themselves here, right? We've been talking about whether these are high or low, but now we have to talk about these things, right? We already did our DDRD stuff. We already did our data direction register. To read the pins, we're going to use the register pin. Okay, but there's a little more to it. So now let me sort of show you what happens. This circuitry here applies for each and every pin of each and every port. Okay, so you have the pin itself, right, with our external circuit, right? And inside the chip, there's actually an internal pull-up resistor, right? This is an internal pull-up. That goes itself to a switch where it's then tied to 5 volts. Okay, VCC is our 5 volts. And that switch is actually controlled by the port register. So we can use that port register to either keep that switch open, in which case the internal pull-up is not being used, or we can set that port register high, and that will close that switch, and we will be activating the internal pull-up resistor. Okay, so this table down here, which is kind of complicated, summarizes all that's happening in here. So when we're dealing with input pins, the first thing to note is we have to have DDR has to be 0 to make it an input pin. And when we say DDRX, what do we mean? Let me just break that down. DDRXN. This is the language that the data sheet uses, okay? So that means it's DD, R, B, C, and D. Okay, DDRB, and then we'll have pin 0, D, D, R, B, 1, ... to D, D, R, B, 7. That's the data direction register for port B. And likewise, this applies for ports C and port D. So this kind of language here, it really represents every pin and every port. It takes a little bit to get your mind around that, but that's the sort of the shorthand notation that the data sheet uses. Okay, I've got a question. What's the resistance of the pull-up? It's typically around 10 kilo-ohms. I think some reports actually show it as being 4.7 kilo-ohms. So it's around 5 to 10 kilo-ohm. And now, and why is that? Why is it 5 to 10 kilo-ohm, and why isn't it a smaller value? Well, you know, that has to do with power consumption. You know, if you've got your 5 volts here, and then you have this pull-up resistor here, and then your output circuit is, let's say, connected to ground. All right. The current that's going to go through there, I, is going to be equal to 5 volts divided by the resistance. And so that pull-up has a certain resistance associated with it. And Ohm's law tells us that the current through it is going to be 5 volts divided by the resistance. And so if the resistance is around 10K, then that means that I is going to be about 5 divided by 10K, which is about 0.5 milliamps, which is a relatively small amount of current. And the idea is you want to keep the current associated with these internal pull-ups low for 2 reasons. You don't want the chip to get hot, right? Because you're dissipating heat in that resistor. And also you don't want to drain your power supply excessively, particularly when you're running this thing by batteries. Okay, more on that later on when we get into interfacing. So don't stress about that stuff right now. That was just for your curiosity. Okay, so we know we have to in order to read a value of a pin, right? We're going to be looking at the pin register, and so what we're interested in, you know, in our example, right? We were interested in pin D6 and pin D7, right? Because we're using no, that's not right. It's 3 and 4, because our inputs are going to D3 and D4. So we're going to be reading the logic values associated with that by reading pin D3 and pin D4. Okay. The point behind this chart is that by writing to the port register, so I realize we're throwing a lot of registers around. You know, we got the data direction register, we got the pin register, and we got the port register. When the port register is 0, then the internal pull-up is off, and it's what's called the high impedance state. And when the internal when the port register pin is set high, then we're activating that internal pull-up. Okay, why is it called high Z or high impedance? Well, you learn from circuits, right, that when you look at the resistance, or when you include the capacitance, you call it the impedance of that port. It's really set by the value of that internal resistor. And so when you have that internal pull-up resistor applied, then the internal resistance is going to be 5 or 10 kilo-ohms like we just described. If you open up that switch that's shown there, and this switch, if you open this up and you disable the internal pull-up, then it looks like an open circuit. It looks like a very large input resistance, because an open circuit theoretically is infinite input resistance. And when you bring in the capacitance of it, resistance becomes impedance. So we call that high Z or high impedance. I'm going to break this down in more detail on the next couple slides. Okay, so here I'll sort of break it down for you. So 2 slides. I'm going to show you 2 slides here. I'm going to show you what happens both logically and in terms of voltages for 2 different cases. So I have slide 1 and slide 2, and I'm going to sort of flip back and forth between them. Okay, so let's look at this one first. The situation where we have our switch and I have an external pull-up, All right, I've installed an external pull-up resistor here. Okay, and so I'm setting. I'm going to be looking at what happens on pin 3. Right, I've got my switch. They're connected to pin C3. Okay, so that's pin 3 of port C. Okay, I will have set the data direction register associated with that pin to 0. That means it's going to be an input pin. I would have set the port pin for that pin, right? Port C3, I would have set that to 0, which means I'm not using the internal pull-up resistor. That's what that means. I'm not using the internal pull-up, okay? So now let's just look at what happens. First, let's look at the case when we close the switch. So when I come along, when I put my finger on there and I close that switch, I'm making an electrical connection there. And when that happens, PC3 is wired directly to ground. So PC3 is at ground, right? You would measure 0 volts with a meter. And so when you read pin C3, the logical pin on the input, you would read a 0. Now you take your finger off the switch and you open it up, right? You're breaking the connection. PC3 is now pulled high. It's pulled to 5 volts. Okay, so PC3 is 5 volts. You would measure 5 volts with a voltmeter. And what we would read would be a logical 1 in the processing that we're going to do a couple slides ahead. Okay, so that's the case where we have our external pull-up. And so we're looking simultaneously at the electrical voltages in the physical world, and then we're looking at the digital values, the bit values 1 and 0, in the cyber world, inside the chip itself, in the memory registers inside the chip. Because see, everything that happens in the chip is happening in patterns of 1s and 0s. Things are only going to be 1 or 0, and they're going to be in different bit positions, but all that stuff inside the chip is nothing but 1s and 0s. Why is that? Because the chip is just a large number of transistors, and transistors are either off or on. Okay, so everything inside the chip, 1s and 0s. The physical world, though, that's where we have our voltages. Okay, now let's look at case 2, where I get rid of that external pull-up. Right, so the same situation, but I have no external pull-up. I remove it, and this is the case where we have the floating input. Okay, so let's first look at what happens when I close the switch. I come along with my big fat finger and I close that switch. All right, and when I do that, PC3 is going to be connected directly to ground. Okay, so I have 0 volts, and I would read a 0 on the logic side when I read the value of the pin register. Now, when I open up the switch, I remove my big fat finger from it, open it up, right? What is the value of PC3? You walk up there with a multimeter and you measure voltage. You don't know, is it going to be high or low? That's our floating situation. And when it's floating, you don't know whether you're going to read a high or a low. You'll get a value, but you just don't know whether it's going to be high or low. Quite often, what it'll do is it'll bounce around. It'll sort of be, it's undetermined. You'll get a garbage value. Okay, so that's the case where we looked at what happens with an external pull-up, and then we looked at the case where we took away the external pull-up. Now I'm gonna go to a new slide, and the top half is going to be exactly the same, but I'm going to change the bottom half. Okay, top half, right? This part up here is going to be the same, but I'm going to have a different bottom half. So here it is. Okay, so this was if I went back, I called this cases 1 and 2. This would be case 1 again. All right, where we have our external pull-up, and everything is exactly the same as it was. The new thing, and I want to call this sort of piece 3, is I've activated the internal pull-up. And the way I do that is I simply put a 1 in this position here, in the port C3 position. And I'll show you code that does all this later. But by putting a 1 in there, I'm closing that internal switch and I'm activating that pull-up. And when I do that, right, look at what happens when, look at the case when the switch is open, right? This is where we had trouble before. When that switch is open, what's the value that you have right here? What's that voltage? Well, it's going to be pulled high. It's going to be pulled up to VCC, which is 5 volts internally. So you'd have 5 volts on there. So you'd have a clean 5 volts. It wouldn't be this sort of extraneous, don't know what it is because it's floating. And that would give you a 1 on the logic side. Okay. So now let me just sort of remind you here, we don't actually, when I write all this stuff, these are not C statements, right? I don't mean to imply that these are C statements. We're not allowed with our compiler to go in and set the level of any particular bit. The AVR GCC compiler and toolchain only allows us, when we're writing C code, to set the value of an entire byte, right? To set the value of an entire register. So we have to, in one fell swoop, we have to set all the pins in the data direction register or the port register or read from the pin register. We do it all at once. We access the entire register, all 8 bits at one time. We can't go in and address them individually in C. If we were writing in assembly language, we could actually go in and target the individual bits. And so because of that, we use the kind of fancy constructs that we've been looking at, where we want to go in and surgically target one bit, set it high or low, even knowing we have to simultaneously do something with all the bits. And so that's why, we were using these sort of funky kinds of commands that we've been, creating, the and equal and the or equals, which we just looked at previously. Okay. So now let's go in and look at how do we actually, what does the if statement look like to check whether a particular bit is high or low? Let's assume that we've correctly hooked up everything, on the outside, and we have our pull-up resistors in the right place, right? So if fingers on the switch, then that input pin is going to have a higher or low voltage, and that's going to give us a higher or low bit position in pin C. Now what I want to do is I want to test. How do we create code that will test whether that pin is actually high or low? Okay, so here's how I want to do it. I want to first start out by, let's check. I'm going to check to see if let's say bit 5 of a particular byte is high. So let's suppose that I have this byte here, and I just want to know, is bit 5 high or low? I just want to find out that. That's what I want to know, because let's suppose that corresponds to this pin that's sensing a switch in the outside world. So how do I find out if that's high or low, given that I can only read the entire byte? Well, the thing I need to do is this next step, is a bit by bit and with a mask. And it's going to be a mask that has a 1 in the bit 5 position and 0 elsewhere. Why do we do that? If we take this byte and we do a bit by bit and with a mask that has a 1 in that position, what we'll end up with is zeros everywhere else and an X in that position. That's the position that we care about. So we've deliberately zeroed out everything else, and we will only have that bit 5 that's left. Okay. Now, if bit 5 is high, we'll have a 1 there. And if bit 5 is 0, we'll have a 0 there. So the result of this, the value after we do that, okay, it's going to be 0 if bit 5 is 0. And it's going to be non-zero if bit 5 is 1. Okay. So how would we write a piece of code that, using what we just talked about, we want to check the status, 1 or 0, of pin C5. I want to know if let's suppose I have something hooked up to C5, right? I have a 0 or a 5 volts on C5. I'm going to read pin C, and I want to know if bit position 5 has a 1 or a 0. So this is what I would do. I would have this if statement here. I would take pin C, and I would AND it with a mask that has a 1 in this position. And what that's going to do is it's going to zero out all the rest of the bits, and it's only going to check the value of that 1 bit position. And we're going to see, let's see if the result is not equal to 0, right? So I can check if it's not equal to 0. That'll tell me if bit 5 of pin C is high. Okay. The next line is the next 2 lines are just shorthand ways of saying this, because as we've seen many times by now, this is the same as this, right? The 1 shift left 5 is a way of getting that mask. So from this line down to this line, we're just using that shift left operation. And then down to the next line, we're just making it look pretty by replacing that with pin C5, because that's this sort of self-documenting thing. So this would be the construct that we would use if we want to see whether pin C5 is high. This code right here. If and it's easy to not get the right number of parentheses when you do that, because there's a lot of stuff that's nested inside here. But what we're doing is if pin C and one shift left pin C5, all of that that strips out, and it sees whether the bit position C5 is high or low. And by checking if it's not equal to 0, we're looking to see if it's high. Or we can check to see if it's equal to 0 to see if it's low. Okay. Now, one little subtle thing here, if you've been able to follow along with this, right? Notice that I'm checking if it's equal 0 or not equal to 0. Why don't I check to see if it's equal to 1, right? Why do I not do this? And this is sort of a tricky little thing. Why would I not check to see if it's equal to 1? Well, assume that I do have a 1 in that position, right? Assume I have a 1 there. What is the value of that? 0, 0, 1, 0, 0, 0, 0, 0. That's binary, right? What is that equal to in decimal? It's 0, 1, 2, 3, 4, 5. It's 2 to the 5th, which is 32. This is deceptive here, right? The reason why we don't check to see if this whole thing is equal to 1 is because I have a bit shoved way up into bit position 5, right? And so that would represent a decimal number of 32. Okay, so some examples. Let's do a couple of examples to sort of make it all come together. Okay, so a switch with an external pull-up is connected to pin PB0, and an LED is connected to PB5. Write a program segment to get the status of PB0 and send it to the LED. Now, I took this from, I think I took this from the textbook, but get the status of PB0. What do we mean by that? We mean if I have a 0 here, then I want a 0 here. If I have a 5 volt here, then I want a 5 volt here. Okay, and so what I want to do is I want to sort of transfer the status of PB0, which is different from the switch, right? It's actually the opposite of what's happening with the switch, and here's why. If when the LED is on, right? We tend to think about our intuition for something like this is you put your finger on the switch and the LED goes on, right? But there's actually a reverse logic. Put your finger on the switch and you're going to have PB0 go low. So there is a reverse logic that's built into this, which is a little confusing, right? You put your finger on the switch, you're bringing PB0 to ground. PB0 is going to be low. And the way we were asked to write the code is we're getting the status of PB0 and sending that to the LED. So it's an example of reverse logic. But anyway, let's just go through it. Okay, what I need to do is I need to make PB5 an output, and I'll make all the other ports as inputs. So that's what this line here will do. Okay, it'll give us one of those pins as an output, the rest are all inputs. And then I'm going to get in my do loop here, or my while loop, and I'm just going to stay in this forever. And I'm just going to check to see if PB0 is 0, using what I just described on the previous slide. If it's 0, I'm going to make PB5 equal to 0. If I'm testing whether PB0 is 0, right? And if so, I'm going to make PB5 equal to 0. Otherwise, I'll make PB5 equal to 1. And I won't spend the time to unpack all this. We've done that on previous slides. But this would be an example of simple code that would transfer the value of PB0 over to PB5. Okay, another example here. Yeah, I'll show you this one. The thing that's different about this one here is we don't have an external pull-up. So let's look at the statement of the problem. A switch without external pull-up is connected to pin PB0. an LED is connected to pin PB5. Write a program segment to turn on the LED when the switch is pressed. Okay, so now let's think about the logic. I want to turn on the LED when the switch is pressed. So when I press the switch, PB0 is going to be 0. I press the switch, PB0 will be 0. But at that time, I want the LED to go on, so I have to have PB5 go high. So the logic here is that PB5 is the complement of PB0. Okay, so I just wanted to make that note here. All right, we have to make PB5 an output and the rest of them as inputs. The only difference between the previous code and this one, or not the only, but a key difference here is I'm going to activate the internal pull-up on PB0. All right, buried back in the previous slides, I showed that this is how you would go ahead and activate the internal pull-up on PB0. So when you do that, you would provide that pull-up that you need to avoid having a floating input. Okay, and then the rest of it is a similar code. It's just going to cause things to go high or low depending on whether your finger's on the switch. Okay, finally, the last thing I want to show today is the code for this app that I had at the very beginning. I won't break down the code in any detail except to sort of show you that I've activated pull-ups on both of those inputs in this code, and it works, right? And so on the circuit, you may recall I had a pull-up on this one, but then I had no pull-up on this one. So on the input side, I need to put a pull-up on the one that doesn't have a pull-up and a pull-up, right? But it's okay if you actually activate the internal pull-up and you have an external pull-up. That's going to be okay. What I do when I'm working with switches like this is I would activate the internal pull-up, and that simplifies it, and I don't need that external resistor. It just makes the circuit simpler to work with, right? And I'll show you what I mean by that. Go back to this one here, and we'll just sort of expand the size of this. Okay, this one here has a pull-up resistor, and what's required for us to make that happen? Well, I had to actually bring the 5 volts, right, from the Arduino over, set it up on a voltage rail, and provision 5 volts on the board so I could put that resistor in there. It's not a whole lot of work, but it's an additional resistor, an additional wire, an additional thing I got to keep track of, right? Whereas if you look at this one here, all we have is our switch. When you press the switch, you're making an electrical connection between the black wire and the orange wire. It's just simpler, okay? So many times when you're designing something, you want to do what you can to simplify it. You don't want to oversimplify it, but you want to simplify things. And if that means that you can conveniently find ways of not adding additional pieces of hardware, then it results in simpler to build, test, and maintain. So when I'm doing these things, I would tend to use the internal pull-up unless I have a compelling reason not to. Okay, that's it for today. I'm going to let you go early, but I will. So I'd say let's spend a minute if we have any questions. And then after that, after a few questions, I'm going to sort of let you go, but I'll stay on the line if anyone has any extended questions. So are there any immediate questions you want to ask right now? Okay, so class dismissed. Enjoy the rest of your Wednesdays. Beautiful.